Hi, in this video, we want to take a look at synthetic data. And what we want to do, we want to look at different algorithms for generating synthetic data, and then we want to compare them somehow. So what we're going to do is we're going to go through, we're going to take some imbalanced data, and we're going to generate synthetic data. Then we're going to use the synthetic data to build models. And then we're going to use the same model structure on all the generated data sets. And we're going to look at the accuracy or the area under the curve for each of the models. And we're going to use that to determine or to judge the quality of each method for generating synthetic data. All right, so when I have unbalanced data, I'm in a situation where the proportion of observations for a target variable, a categorical classification supervised learning problem, the target variable is not proportional to how I want it to be. Either it's not representative of the population that I know what it should be, or I feel like I don't have enough of a less frequent level proportionally. Okay, so in this situation, when I have unbalanced data, I have four major options. First one is to adjust weights. Second one is to downsample the majority class. Third one is to upsample the minority class. And then the fourth one is to generate synthetic data. And that's the order in which I feel like we should use them. I feel like weights is the most important and synthetic data is the lowest. Now, I feel like synthetic data is not a good option compared to others, but it's still a tool that we should have in our tool belt. All right, so what we're going to do, we're going to partition our data for twofold cross-validation. Then we're going to generate synthetic data to have a one-to-one synthetic to original data. Now, this is on the minority level. I feel like more than one-to-one, you're just generating just noise, not noise, but you have too little of the observations, so that if you're doing more than one-to-one and you're fitting on, not on your data, but on your synthetic data. So I feel like you should stop at one-to-one. If you don't have enough data after a one-to-one ratio, then I feel like you should look at weights, look at downsampling, and look at upsampling. Then after that, we're going to perform twofold cross-validation. And so something I need to say about the synthetic data, after I partition the data for twofold cross-validation, I'm going to generate synthetic data here. I'm going to generate synthetic data here, only on the minority cases, and I'm not going to cross over. That way, my twofold cross-validation, I don't have overly optimistic values in my cross-validation statistics. And then we're going to compare the results using area under the curve from the ROC. Okay, so let's go ahead and load the data. So here we're going to use the yeast4 dataset from the imbalanced package within R. And our target variable is going to be class. Now for some visualizations to make sure that class comes up, I went ahead and I sorted the data by class. If this was a big data project and I wasn't going to be visualizing like I am in a moment, I would not perform the step. Here I convert this factor, this two-level factor, into a binary. And this vector is just the numerics vectors, and this is all of the predictor variables. And you'll notice that the factor that was converted to binary is included in here, but not inside numeric. All right, so now let's go ahead and let's take a look at the data. All right, so we can see that the data, roughly speaking, all the predictor variables that are numeric go from 0 to 1. All right, so that's nice because now that we know that the data is, within the same range of values. Now I look at the target variable, we can see that we only have 51 positive cases, and we have, over 1,400. So that means that we have 3% positive cases. Now, that might represent the actual true situation of the population, but 51 is proportionally very low, 3%. It's going to be hard for me to build a model that detects the positive on this one. Now, so I need to do something about it. I don't have enough of a signal in there for the modeling structure to detect positive cases. Now to get an idea of what's going on with the data, let's go ahead and run pairs. And what I do here, when it's positive, it's a red circle. When it's negative, it's a black circle. And this can give me an idea of the distribution of my data if I look through. Now let's partition the data. So I'm going to go ahead and I'm going to do twofold cross-validation. So I'm partitioning into two sets. Now, why do I do twofold cross-validation? I like that a lot because when I build a model with twofold cross-validation, the sets are completely, or the models are completely disjoint from each other from a data point of view. If I was to do tenfold cross-validation, then 8 out of 9 of the data for any two models that are built on the cross-validation process, 8 out of 9 of the data overlaps. And so I'm not really like separating out the models as much. So I like to do twofold cross-validation. So I have two sets, and every single time here, like this is a training set, this is validation, then this is training set, this is validation, and it works nicely. If I want more for this than what I would get from just two, I can also do repeated cross-validation if need be. Also, something that's nice about this, in contrast to, let's say, like tenfold cross-validation, when I have less data, if the model structure takes a longer time, like an increasingly amount of time to fit when I have more data, then doing twofold cross-validation can substantially reduce the fit time for each of the models. And so that's a good way to go. Now, this is an advantage over doing something like tenfold cross-validation where I'm using 90% of the data each time, and I'm doing it repeatedly. All right, now, so let's generate some synthetic data. So first and foremost, we're going to go through and we're going to have no synthetic data. We're just going to run the model as is. And that way we kind of have a benchmark to compare the other methods. Oh, and as I go through this list of synthetic, at this point, I'm just storing only the synthetic data on there. And then we'll tack on the other data and we'll go ahead and proceed from there. Now, Rose creates a sample of synthetic data by enlarging the feature space of minority and majority class examples. All right, so when I do this, I'm going to have all my predictors or all the columns except partition included in the formula because this signals which variables to generate, where the data is coming from, because remember I got a twofold cross-validation, how many observations to generate, and I want 90% of the observations to come from the minority case in the situation. Then after that, I'm going to only take the positive cases because rows, well, so some of these algorithms will generate negative and positive. And so it's possible that if I wanted synthetic data, I could generate positive and negative cases when I do my modeling. Here, I only want the positive cases just because that's my, my minority case. And then I restrict it down to a smaller size just so that I'm gonna make sure I have the same number of synthetic values in each of my data sets. Now here we're doing SMOTE from the data mining with R package. So we're artificially generating new examples of the minority class using nearest neighbors of all the cases. Specifically, we've got 5% for the number of nearest neighbors being used and percent over. So I'm oversampling the minority case and the percentage is 1,000. So that's quite a bit. So I would end up getting a lot of values for this. But when I go through and I remove extra values, it's going to be trimmed down. So I have approximately the same number of values coming out from each of these methods. And percent under is the percent of the majority case to sample, which I set to 0 because I don't want to waste time on the majority case. Now we've got adaptive synthetic sampling approach for unbalanced learning. And so this is called Addison. And the number of majority neighbors of each minority instance determines the number of synthetic instances generated from the minority instances. All right, so it uses so what this tries to do, this takes an observation and it looks to see, is this like a boundary observation in terms of higher dimensional data? If it's a boundary observation, then that's going to be one that wants to be generated, because really when I do a lot of classification models, I just need a solid boundary in higher dimensional space. And so this is working hard to just form like kind of a shell around all the values that are from the original data. Next, we have adaptive neighbor synthetic majority oversampling technique. So we generate oversampling data set from the imbalanced data set using a adaptive neighbor version of SMOTE. And it provides K is the number of nearest neighbors, or not nearest neighbors, but adaptive neighbors included in the generation. Now we have borderline SMOTE. So once again, we're trying to get the borderline cases. The borderline cases are the ones that are most important to us, because if I have a good solid boundary between my positive and my negative cases in terms of higher dimensional space, I'm going to have good model fitting. So here we generate synthetic positive instances using a borderline SMOTE algorithm. And what it does, it breaks it partitions each of the observations into one of three groups: safe, danger, or noise. And only danger is used to generate synthetic instances. All right, so safe means it's if there is a higher dimensional space of my minority case. And if I pretend, if you think of them as like being like in maybe let's say a sphere, the ones in the middle are safe. Like it's like the model is not gonna have any problem fitting those guys. Danger are the ones that are like on the boundary, and the noise are the ones that are like outside that shell. So danger are the ones that are like my borderline cases. And so what I want a lot of borderline cases to fill in the parameter or the higher dimensional space. Next, we have density-based SMOTE. And so here it uses the density to generate new data. This one gives a lot of output. Yeah, I'm not real sure what's honestly going on with that, but yeah, it's all good. Now, next one is relocating safe level. So this is RSLS SMOTE. And once again, it figures out like a safe level to determine possible, candidacy for generating new data. And then here's safe level without the relocation. And this does something similar, that it determines like a safe level and then uses that to determine if a point should be used in the generation of new data points. And now here we have SMOTE. Now this is a different SMOTE than we looked at before. Previously, we looked at SMOTE within the data mining with R package. Now this is SMOTE within the SMOTE family package. All right, and this performs very similarly to all of the other SMOTE family functions that we've taken a look at. All right, so now what we're going to do, we're going to take all the data points that we've got, and we're going to go ahead and we're going to combine the original data set with the synthetic data. And so all of the negative cases will be the original negative cases. Half of the negative cases will be from the original data. Half of the negative cases will be from the synthetic data. And so remember, I've got a 1-to-1 ratio between synthetic positive and original true data positive. Now let's go ahead and build logistic regression models. And so what we're going to do, I'm going to, on each of the data sets that include synthetic data or the original one also, what we're going to do, we're going to build a model on the first fold, validate it on the second. Then we're going to build a model on the second and validate it on the first. And we're going to do that for every single algorithm that we've come up with. And then what we're going to do, we're going to go ahead and take a look at the area under the curve and the ROC. And there's a lot of output. Let's go ahead. And what we really want to see is the output here. So remember, what the ROC does, this gives me a visual representation of different cutoffs that I could possibly use for saying if this is going to be a positive or negative case. All right, so if I have a model that gives me a probability from 0 to 1 of positive or negative, what I can choose to do, I could say if it's greater than 50, it's positive. If it's less than 50, it's negative. But I don't necessarily have to. I could say if it's greater than 0.75, it's positive. If it's less than 0.75, it's negative. I could also go, if it's greater than 0.25, it's positive. If it's less than 0.25, it's negative. Okay, so I have, along a continuum, infinitely many values that I could actually cut off for classifying. Well, if I reduce the criteria for saying positive, then I'll rarely miss a positive case, but I will be introducing more than likely false positives in there. Other way around, if I make the criteria for declaring positive very high, then I'm almost never going to miss a negative case in my modeling, but I will have more false negatives. And what this curve does, the closer this curve is to the upper left-hand corner, basically the better you know that the criteria is going to be. Each dot along this curve represents a different criteria that I could set on from 0 to 1 to make a declaration. Ideally, this curve would follow all the way straight up, touch this corner, and then go horizontal over here. And you'll notice that this is always a non-decreasing function as I go from left to right. All right, so when we use no synthetic data, we have an AUC of 0.88. All right, now let's take a look at using rows. When I look at rows, the AUC actually went down. It went down from 0.88 to 0.86. That's not very good. That kind of defeats the purpose of generating data, right? I went through all this work and I get a worse model. That's awful. Now, when we do a smote from data mining with R, we can see that we have 0.88 again. So we really got no improvement from that algorithm. Here we have ADAS, and we see it's 0.89. All right, that's a little bit of an improvement. So ADAS is our best one so far. Then ANS, we got 0.91. That's our best. BL smote is 0.93. All right, so that one is our best so far. So BL smote is our leader. Then when we look at density-based smote, it's 0.91 and 0.92, which, is stronger than others, but not our best. Now we have RSLS, it's dealing safe level smote, relocation safe level smote. And we have an AUC of 0.93. And then safe level smote, we have an AUC of 0.93 also. And then the smote family smote is 0.81 or 0.82. Okay, so let's take a look at how that compares in a bar plot. All right, when I look here, first and foremost, just not using any synthetic data did better than rows and did better than smote family smote. All right, so we know that for this problem, I absolutely would not want to use either one of these techniques. Now, when I look at smote from data mining with R, it's a little bit better, but not by much. And then we have a little bit of improvement with ADAS, then ANS, and it keeps on getting better until really I would be looking at one of the two safe level smotes or the boundary level smote. These look like they'd be the best option for the problem I'm working on. All right, well, that's all I've got for you. Take care and goodbye.